I'm Lee, this is Jump. Let's look at some graphs. I've got four pairs of points here, x1, y1, x2, y2, x3, y3, and so on. And I want to look at the line of best fit for each one of these pairs of points. Well, here are my graphs, and you can see that the lines look similar. Let's look real carefully at the equations. Y equals essentially 3 plus 1/2 x. Down below, y equals 3 plus a half x. The third one, y equals 3 plus a half x. And the fourth one, y equals 3 plus a half x. Let's also look at the r square, the measure of the strength of the linear fit of these lines. We have the first one, r square equal 0.66. Down below, r square equal 0.66. R square equal 0.66, and the fourth one, r square equal 0.66. If we look at the F probability, the goodness of fit statistic, we see F equals 0.002. Scroll down, F equals 0.002. Here, F equals 0.002, and down here, F equals 0.002. In essence, you've got four graphs, four sets of data with identical equations, identical t-values, identical r-square values, identical f values. If you were a doctor and had four patients with identical symptoms, how would you diagnose them? In this case, they're not similar at all. Let's look at the points. If I show the points on y1 and x1, you'll see that it's a pretty typical regression situation. We've got points clustering around a line here. If I look down at x2 and y2, however, I've got a very different situation. This is not a case where a line is the best fit. You can clearly see that this is a curved set of data, and in fact, if I fit a second-degree polynomial, a parabola to it, it fits perfectly. It doesn't really matter that it's a parabola, but it does matter that it's not a line. If we go back up here and look at x3 and y3, we'll see that when I show the points, that we've got one point that's sort of exerting a lot of pressure on this line. Everything else falls on a perfect line except for this one point. If I exclude this point, we will see that if I can fit a line perfectly to the remaining points. So I would go back and look at this point in my data, see if maybe it's a little off or if the measurement was taken wrong, because it's exerting a lot of influence on this line. If I look at the last set of points here, we've got an even more extreme situation. We've got a set of points all along a vertical line and one point that's exerting absolutely all of the leverage on this fit. I can show you that a little better with my least squares demo. If I plot the least squares line on here, you've got all those points along this vertical line and one point way far away. And wherever I drag this point, the least squares line follows. It is absolutely determining that equation, that fit. So the lesson for today is to always look at graphs because the numbers aren't going to give you the whole story. I'm Lee. This is Jump. Thanks.